Okay, so if you have any questions as we're going, just stop me. Right. Oh, there we go. Okay. So example 3 is a really common like optimization problem. Remember how like related rates, like I told you guys, the ladder problem, super common related rates problem. Like every textbook, calculus textbook usually has a ladder problem. Every textbook has a box problem. And if any of you guys have really good memory, you might even recognize one of these types of problems from like pre-calc and like a quadratic word problem. So this problem could actually be solved using algebra. But we're in calculus and we're gonna practice using our calculus techniques in order to solve this problem. So we're given that an open top box is made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. So if you're having a hard time visualizing what this is saying, okay, so here's my, will this work? There we go. Okay, so there's my piece of tin, which is 20 by 25 inches. So like these sides are 20 inches. The longer sides are 25 inches. And what's going to happen is we're going to cut squares. So saying we're cutting congruent squares or squares that are the same size out of each corner. So we're going to cut like a square out of that corner. I guess I could, I'll just draw it. Of that corner, and that corner. And all those squares should be the same size. So meaning each of those squares would be x by x or whatever variable you want to use. So x by x, x by x, x by x, x by x. And then after those corners have been cut out, folding up the tabs on the side. So like folding up along here, along here, and along here, and along here. So that you would have something that might look like, let's see. Right, so something that might end up looking like that. Okay, open top box, like after you've folded up the sides. Now, the question is, how large should the squares be to make the box hold as much as possible? So to make the box hold as much as possible. So what quantity are we trying to maximize or minimize, optimize? What quantity are we trying to optimize?
Volume.
Volume. And we are trying to specifically maximize or minimize?
Maximize.
Yeah, we want to maximize the volume. We want to make the box hold as much as possible, which means we want to maximize the volume. Oops. So since we want to maximize volume, Zach, what's my optimization equation going to be for?
Volume.
Volume. So we need to come up with an equation for volume here. And volume is of a box, right? Of a rectangular prism is length times width times height. So we need to figure out how we're coming up with our volume equation that's length times width times height. So we need to figure out what the length, width, and height are. Now, if we cut out those squares that are x by x from each corner and fold up the sides, do we see that the height would be x? The height of the box would be x. So that's going to be one factor. And then how can we come up with the length and the width?
Would it be 20 minus x and 25 minus x?
So close, but you're on the right track. The thing is, how many x's are we cutting out on each side? Did you say 2x?
Yeah.
Okay, perfect. So on the longer side, we usually refer to the length as the longer side, would be the 25 minus 2x. Does everyone see that? That we're cutting out an x and an x from each side. So we're actually cutting out a length of 2x from each side. And then our width would be 20 minus 2x. So that's length times width times height, or I have it written as height times width times length, but that works. Okay. Now here's the cool thing. Our volume equation, our optimization equation is written in terms of a single variable. So you guys, we don't need a secondary equation for this problem, which is nice. What we do need to do is multiply this guy out to find the derivative. And you could either multiply it all out at first. It's kind of like, when do you want to do all the multiplying? So we could either multiply out everything, or we could just distribute this x into one of the factors, just one of the factors, and then use product rule. Maybe that would actually be more efficient. So we would have 20x minus 2x squared times 25 minus 2x. And you only distribute into one of the factors. And if anyone is wondering why we only distribute into one of the factors, remember that each of those factors represents a number. So like if you were to think about having like 2 times 3 times 5, you wouldn't distribute the 2 to the 3 and the 5. You could think of that as being equal to, well, 2 times 3 is 6 times 5, right? Which then 6 times 5 is 30. So you're only distributing the x to one of the factors, and you can choose which factor. And then you could multiply this out. What do you guys want to do? Do you want to do product rule, or do you want to multiply this out to use power rule? Do we have a preference?
Not really.
Not really. Okay, well, let's just use product rule. Just change it up a little bit. So V prime would be the first factor times the derivative of the second factor, which would be -2, plus the second factor times the derivative of the first. Okay, and then at this point, we would want to multiply out our derivative, but I don't know if you would consider that to be nicer or not. So we could distribute the -2. So negative 40x plus 4x squared. And then when we multiply out, it's 25 times, 500. Oops. So 500, and then distributing to the -4x, that would be minus 100x, right? And then minus 40x and plus 8x squared. And then just combining like terms, that gives us 12x squared minus 180x plus 500. Yeah. So that's our derivative. Our optimization equation is a polynomial. The derivative is a polynomial. So for finding critical values, we're really only going to need to think about setting the derivative equal to 0 and solving. Before I do that, does anyone have any questions on any step? Okay, so I'm going to set my derivative equal to 0. Gosh, the GCF. Is there a GCF bigger than 2? I know I can factor 2, just 6. No. Well, let's factor 2 out just to make our lives a little bit easier. Or we could factor, actually we could factor 4 out, huh? Factor 4, let's do 4. So 3x squared would be 45, wouldn't it? Yeah. Okay. At this point, you can divide out the 4. So like this could just be 0 equals 3x squared minus 45x plus 125. If you guys wanted to go directly to quadratic formula because that's what you're comfortable with and not even worry about factoring out, that's fine too. That would work. I just prefer to work with the smaller numbers if possible. I don't think this is factorable. So using quadratic formula, which you all should have memorized, maybe you sing the song to yourself, right? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so one of our values that we would want to be a critical value would be 45 plus 45 squared minus 4 times 3 times 125 plus the square root of 525 divided by 6, or we would have x equals to 45 minus the square root of 525 divided by 6. These are the values we want to be our critical values. I know they're yucky looking, But before we can determine whether they're both actually critical values to go on the analysis line, we need to think about the constraints of the situation. So this is one of those, our optimization equation is a polynomial. When it's possible to define your optimization equation on a closed interval, you want to do that because then you can just do the table for extreme value theorem. Yesterday, Trevor asked a really good question about if you didn't come up with that closed interval, or like, could you use first derivative anyways? Like regardless of what the situation is, like in the fact that you can come up with a closed interval, could you use the first derivative test? Yes and no. And the thing is, you have to come up with the constraints. You have to think about what the constraints of the problem are. I'm going to check with Mr. Green just for students that are taking AP next year on what his thought is on that and like what the AP's thought is on that, like using the table versus first derivative test. Like if you're able to use the table and come up with the closed interval. I want to say that the only time that it would be okay to use first derivative test is if you still took into account that closed interval and did an explanation, an extra explanation. But I'm going to double check with Mr. Green, talk to him about it, and I will get back to you guys on that. So for now, I'm going to say that it's better to do the closed interval. So going back to our volume equation and our picture and thinking about the situation. Now, if we let x equal to 0, the volume would be 0 because we would just have that flat 20 by 25 inch piece of tin, which volume being equal to 0 is possible, right? It doesn't really make sense for this situation since we're trying to maximize volume, but it's possible. There is a limit to how large x can be. If you're thinking about cutting x inches onto each side, especially thinking about the shorter side of the piece of tin, what's the largest x can be? What is the largest x can be? X represents how far you're cutting in on each side into the piece of tin.
10.
10. Who said 10? Drew?
Me, Drew.
Yeah. And Drew, how did you come up with 10?
Because on the side of 20 inches, you can only go like 10 in on each side.
Perfect. Yeah, on the shorter side, if you cut 10 inches in on each side, you would just be cutting those strips off. So then you would just end up with, well, a flat piece of tin again. So the largest, we can say the largest that x could be would be 20, and our volume would be 0 at that point. So 0 when x is 0, and then 0 when x is equal to 20. But we can use those as endpoints, right? And that can also be written in interval notation if you prefer. But doing that allows us to do the table. We also, in determining what our actual critical values are, we want to look and see which values lie on that interval, right? Because those are the only values that could be possible points of absolute extrema. I don't know about you guys, but I don't know what 45 plus the square root of 525 divided by 6 is, but I can get the decimal approximation. So I'm going to type it into my calculator so that I have a better idea. Okay, so when it's 45 plus, that's approximately 11.319 versus if we're subtracting, that's approximately 3.681. Well, X has to be between 0 and, it should be 10. I'm sorry, you guys said 10. 0 and 10. X has to be between 0 and 10. So that means that the critical value that is over 10 can be thrown out. So then when we do our table, I'm going to give myself an extra page just so I'm not scrunching everything. When we do our table, to see what would give us the largest value, right? We use our endpoint of 0, our endpoint of 10, and then our critical value, use the exact value. So use 45 minus the square root of 525 divided by 6. If you want to store that under a letter, like if you have, just going to type it in here again. So if you have 45 minus the square root of 525 divided by 6 typed into your calculator, you can store by hitting the stow button. Has the little arrow next to it. And then you hit alpha. And you choose a letter that you want to store. So like if I store under A, the letter A, I would be hitting the math button. And then I hit enter. And the reason that you might want to do that is just so that you're not having to type that ugly value into your volume equation. So I know volume is 0 when X is 0 or 10, but then if I want to type in using the stored value, that would be A times 20 minus 2 times A. And then it's just hitting alpha and A, or whatever letter you store under. So I get approximately 820.528. So obviously that's the maximum, the absolute maximum volume. Our question was not asking for the max volume. It was asking us to maximize volume, but the actual question is asking for how large the square should be. So that's X. So we can say to maximize the volume, of the box, the squares must be approximately 3.681 inches by 3.681 inches. Or something like that. You can also use the exact value in your sentence if you prefer. Okay, 1 and 3 are very similar to this example. So you guys have 1 and 3 to try. And then number 7 is a little bit more complicated, but I want you guys to give it a shot. See if you can get it. I'll give you a hint. You're trying to minimize the total cost, so you'll need a cost equation. So see how it goes. And I'm thinking number 7 we'll probably want to go over together next class, but we'll just